Hello. So I probably should zoom this a little bit. I was hoping I won't have to because you will see. But anyways, yeah, I kind of tend to dance around a little bit. So let's put this here. So hello. When I saw that my presentation was up on the end of second day, I was like, oh, damn it. Now I have to boil here for 2 days. Last time I did it in Greece was very nice. I got it done by the end of day one, went directly for beers, and then could just chill out for the rest of the event. But I'm actually pretty glad that the timing is what it is, because there have been a number of presentations that I can kind of refer back to now, since there's a little bit of an overlap, some cool ideas that have been brought out. So this is the topic, and let's get into it. So as I mentioned, I did a presentation back in 2022 in Greece about how to use Jupyter notebooks to analyze SuriCata data. So you can kind of think of this as the continuation of that, but I am digging into just one type of data. And this is really something that I've been kind of looking into on and off between other things. And it's something that I feel is grossly underrepresented. Because, well, I'm going to talk about threat detection without rules. So in the agenda, so I'm going to talk a little bit about the SMB data from SuriCata. Not really about the protocol so much, but we'll get into that. I'm going to show you some interesting hunting samples, and hopefully I will get around to also showing you some cool data wrangling and analytics tricks you can actually use to apply on this, like not just on this kind of data, but you will see this is a pretty rich source. So yeah, let's get into it. I always feel like I don't have enough content, and then I kind of go way overboard, so I will try and see how it will actually work out, because analytics is a whole different rabbit hole to get into, so I might kind of fly over this depending on just the timing of everything. So a few words about me. So everybody has a professional picture. Luckily my daughter was nice enough to take one of me. I started my professional life as a server admin. That really didn't like hold me on for too long. I pivoted towards cybersecurity in a master's program. From there, I kind of got involved with some cyber exercises and local Estonian community, which got me my next job, which was a tech branch researcher in NATO CCD-COE, which is a think tank located in Estonia that does exercises, classroom trainings, and well, research. My specialty was threat detection monitoring, which is a huge umbrella, and it was just me and my colleague that basically specialized on it. So, you know, we kind of picked and chose our battles. We chose to kind of focus on the security tools and making friends within the security communities. That is how I met Eric LeBlond. We got him involved in doing classroom trainings on SuriCata back in 2016. And then later we also pulled in Peter for some exercises, and then when I kind of felt like it was about time to move on, guess where I landed. So now I work with those guys. Well, my official job title, I don't know how official it is, I think it was in some email or contract, says threat researcher and software engineer. But, you know, we're a small company, everybody wears many hats. I would describe myself more of a, let's say, forward-thinking hacker than really a programmer. It's a development, like, we are a software shop, we develop a product, so coding is where, like, most of the time goes to. but my speciality isn't so strictly defined within, let's say, front-end, back-end, sysadmin, this kind of stuff. It's mostly just focused around working with data, which means I kind of hop between, I'm sort of a weird mix between a DevOps engineer, threat hunter, data analyst, back-end developer, you know, this kind of stuff. And within the context of this talk, I am not a Windows guy, so if you're expecting a deep dive into the SMB protocol itself, then that's not going to happen. More on that, because we need to move on. So, so what to kind of expect from this talk? No slides, as you can see. Kinda. I kind of try to, the whole point of this talk is to showcase a very rich data source. So I don't want to talk about it, I want to show it. I love Jupyter Notebooks, they're great for interactively showing the data, they're also great for packaging it. So the presentation, Kelly will get the export in, you know, regular, like as regular as you're going to get from me. Everything I'm going to show, I'm also going to package into this open source project we have in Stamos Networks called SuriCata Analytics. I think at least that's what Eric and I decided that that's where it's going to go. It's going to package some data samples. So I have some anonymized and truncated samples from exercises. I'm not going to say which ones, but those who know my background probably have a pretty good idea what I'm talking about. And I also have all of the SMB logs that I was able to parse out from malware traffic analysis, simply because it's, you know, an open resource that I can easily distribute. The hardest thing about preparing this talk was actually preparing the data, because especially when it comes to SMB, we're talking company internal data that nobody really wants to share. Public samples are really small, not a whole lot in there, especially if you want to do like analytics kind of stuff. A little bit of a suspension in disbelief is required here, because, yeah, like to show really interesting stuff, well, I can't really do that. That kind of data is kind of confidential, but I kind of want to show actually what is out there, because not many people even know about this stuff. And also like the technical tricks you can apply on it, right? And there's going to be a little bit of scrolling here, because I'm going to show you some data frames, and it will be fine. Okay, so a few words about what is SMB. Not going to stop on this for too long, because, as I said, I want to show it what is SMB within the context of SuriCata data, not just talk about it. So it stands for Server Message Block, not Samba. Samba is the Linux, Mac OS, Unix implementation of the protocol. And really, it is a protocol used mostly within Windows domain environments to, well, it is the file sharing protocol, right? But it's really way more than that. It is really a remote, it provides remote administration capabilities, all this kind of stuff, hidden admin shares that are often used, and this kind of stuff. Again, I will kind of get into that, but I'm kind of flying over this a little bit fast. Now, just a few words about the SMB versions. I'm not going to stop on this again for too long, but I wanted to show you this simply because it will provide a little bit more context to the samples that I'm going to show. Plus, you know, there's the, in this room, there's always the question about, what about encryption? When is the sky falling? So encryption for SMB was introduced in SMB 3, which corresponds to Windows 8, and most SMB samples I've seen have been plain text. In fact, I looked into it, and Microsoft is currently implementing within the next Windows 11 was like bi-yearly patch, an option for the administrator to enforce the SMB encryption, right? But it's an option, it's not a default policy. So yeah, maybe the sky is falling at some point, but so far hasn't really fallen down. So yeah. And why am I talking about this is really because this is where a lot of very interesting lateral movement type of attacks are happening. So when we're talking about cybercrime, then yeah, like cyber criminals might just want to cash out as soon as possible, you know, like get the malware in, swipe some credit card data, this kind of stuff, and you know, be happy. But more advanced actors, what they do is they will get initial foothold, they will sit around, they will be there for a long, long while, they will try to spread to other systems, they will try to take over systems, and they will try to do it under the radar, right? And in these kinds of campaigns, yeah, signatures, well, well, you might get something from signatures, but really you need to do proactive hunting to catch stuff that might be, let's say, out of profile from the normal usage of the workstations, right? And yeah, you can kind of think of these kinds of threat actors kind of as a cancer spreading in your network. Like it will start growing very slowly, spreading as much as they can, biding their time, not really like doing much at all initially. And yeah, and by the time I would actually argue that, you know, like by the time something like an APT IOCs get out, like I don't think they're that relevant at that point anymore. You kind of need to go back in time to index data to see, have I been compromised in the past? Because, you know, as soon as the signatures come out, like, are they really going to reuse that infrastructure? Maybe for misdirection? Who knows? So, okay. So why do I want to highlight SMB protocol and SMB data in particular? And this is where the code and where the tell kind of ends and the show starts. So let's consider a classical protocol that we're all used to, like HTTP. So let's load some data. I have some samples embedded here. And we can see your typical evlog samples here. You know, we have some alerts, we have the protocol event, we have the flow log. In general, what you kind of get, and I don't really like this kind of view because it's a lot of scrolling. I like this view. This is much better. So it's going to take a little bit of scrolling, but you kind of get the point. We have basically 4 events here for one HTTP connection. We have some metadata that is shared between them, a couple of alerts. We can see that this host name was being accessed. And really what is happening under the hood is, you know, Suricata is processing the stream. It will try to do things as fast as possible. HTTP header is basically getting parsed. That's when you get the HTTP event. During whatever part of the stream, some signatures might fire. Those signatures will give you alerts. And finally, when the flow is either correctly or just like by timeout terminated, you get the flow event that within the next 10, 15 minutes. That's fairly straightforward, and what I'm showing you here is your typical flow correlation. You know, you have your one flow ID for multiple events. And yeah, you can see that all of this info I like to aggregate. You can see one flow ID and some interesting fields. I can see I have alert events, HTTP, flow, and we have also you know, the metadata on top of it. Now let's look at this, like what SMB looks like. So let's load this. I'm going to load a little bit, but because I should have about 89,000 events from SMB, from the MTA samples, which is very small, very packageable. It only took like 2 megabytes in a gzip file. So those samples will be embedded with the interactive version of this presentation for everyone to kind of like play around with and see what is in there. And let's just do a quick aggregation. Let's do some flow correlation. And I'm just doing, and when we look at the event count per flow ID, we're seeing something very different. We see 8,804 events for a single flow ID. We can have anywhere between 1 and to, honestly, a lot. Like, I have seen like 10,000, even more easily. And why is really that and oh yeah, I like to view the statistical view every now and again. So you can see we have very high maximum count here. We got, but in general, normal in this data set is something between 7 and 9 events per flow. And we have some outliers where we only have 1 event or 9,000. Okay. So what is happening? The most important thing to concept here is that SMB is a transaction stream, which means client issues commands to the server, server responds, and each of those commands has its own structure. It is really insane. There are dozens and dozens and dozens of those commands. Some are really not known at all. It is absolutely insane. Yeah, so what is a typical thing that happens is that, for example, the participants will firstly need to agree on a dialect. That's commonly two separate events because not enough information within one packet, I suppose. Then they establish a security context. Usually that is a Kerberos hash, but also it can be an NTLM password prompt, which is actually not that common because in a domain environment you should have Kerberos. But yeah, you can have re-authentication within the same stream. Then the user will need to connect to a tree, which is, you can think of it as a directory or this shared resource, the share basically. And then you perform operations within that tree context. You can create files, you can do remote administration via name pipes and RPC calls. You can disconnect from the tree and connect to another tree. And finally, you can log off, or you can actually just time out. SMB is kind of crazy like that. The spec literally just says, you know, try to reuse everything. So you can see stuff like sessions not really starting properly because the server is kind of trying to reuse old sessions, things like that. Prompting new administration, stuff like that. So let's look at some of them, right? So I'm going to take something within, let's say, the median section here to kind of get not to go way overboard. So as you can see, we have protocol negotiation. Here we negotiated to protocol version 2 of SMB. You can see that's 2 separate events. Then we have the session set up here, which is, it seems to be this is a Kerberos setup, so meaning the security context has already been exchanged before. Where am I? Sorry, there's a little bit of scrolling here. You can see now it's connecting to a tree and performing ioctl commands. In this case, it's actually calling for SMB functions, and finally it accesses some files here. Pretty normal stuff. So and finally, you can see here we have a proper disconnect, proper log off. It's a stream, basically. I'm hoping, let's see, maybe I can zoom this out a little bit because it is a little bit difficult to show such big tables here. Now, let's look at some. So now the question is, where do I even start? Because obviously in a busy network you will have a lot of stuff. If we have like 9,000 events per one stream, like what do I even start looking at? Well, the nasty thing about SMB is that it's really fragmented. You're not going to see each SMB event gives you a small picture, like small part of the overall picture. But some info pieces are always there. So for example, and we can see what we can actually see. So this is a outtake of only the SMB fields within the data set that I packaged here. This is not the complete SMB field set, mind you. This is simply what is here. And this is a common theme with SMB in general. It tends to have a lot of, let's say, obscure events that nobody has ever really seen. And one of the more, and you can really start with the basics. So let's just look at SMB commands and status responses to those commands. So here we can order, the command is kind of interesting here. There is a lot of SMB1 stuff here. But the most important reason why I'm starting off with commands and responses and specifically is cardinality. It's those fields are always there, and the number of unique values is actually fairly small. So commands, yeah, can be useful. Now let's look at the statuses. And here things get a little bit more interesting. What we see here? Well, we see normal stuff, and then we see log on failures, access denied. We see missing responses, which is actually really weird. We have response code 5, which actually means Suricata did not parse it. I know Eric and Victor are going to look at me really weird here, but the fact that Suricata crapped out is a good thing. Why? Because it actually pops out like a sore thumb this way. Hackers do not do things properly. They use old protocols. They use really, really crappy implementation of stuff. So you don't. We are used to thinking about doing things properly, but actually, if you do it properly, then things might actually fly under the radar because status code 5 kind of pops out way easier than whatever is underneath here. And we have other fun stuff here, like unknown 0000000. But that is just from what I was able to get from the public malware traffic analysis data source. There is more. So I packaged here something that I've seen over the course of some years, or from some exercises. And the picture actually gets really interesting. So we have something like this. There is literally an SMB status code saying DOS access denied. We also have stuff like status buffer overflow. Did you know that this kind of stuff exists? Nope. And yeah, all sorts of fun stuff. So let's actually have a look at some of those cases. So firstly, there's this funky status 2121 something something something. And if I do a pullout of this this transaction stream, a lot is wrong. You can already see that it's doing dialect is NTLM 0.12. There's and the native OS claims to be Samba, but actually the way I read it, and this is a common theme, I don't know what the ground truth is. I will shamelessly steal something that Josh said during the malware reverse engineering workshop, is that as a data analyst and a hunter, I know just enough to get by at my work, and then I will figure things out later. And I'm paraphrasing here. What I'm reading actually here is that this is probably some kind of a command line tool, not a Linux workstation. Somebody's probably using some kind of a implementation of a hacking tool that is trying to connect to a name pipe of a Windows server in order to execute commands. The scary thing within this picture as a hunter is actually the fact that beside those funky status codes, I'm actually seeing status success. So I am seeing stuff like SMB1, which should be deprecated on a Windows Server 2022. But I'm seeing status success with other funky codes. This tells me that something has been exploited. Let's take a look at another sample here. Obscure status really makes it pop. what you can see here, again, a lot wrong. Again, like just as I said before, SMB1 should be deprecated, so that in and of itself is an indicator. In here, I would not be as worried, because I see that whatever they're trying to do, they are actually getting, yeah, that's not working. But so why am I talking about this? Well, as Pierre said in his presentation about LDAP, the fact that I am seeing this means somebody is already in the network, trying to move laterally from one system to another, which means your network is already compromised. And this is the part where you need to catch them and kill off the compromise, because otherwise we're going to start seeing other things. Okay, so what else did I... And likewise, Windows 2000 here doesn't really tell me that there's a Windows 2000 workstation there. I actually think that it's most likely, again, some kind of a command line tool with kind of a bad implementation of SMB, trying to connect to a server and, well, not even server. Actually, this is trying to move to another Windows workstation, right? Because Microsoft is nice like that. They expose all sorts of nice remote administration stuff on things that shouldn't, yeah. Let's move on. What do we have here? Here we have a sample of something a little bit modern. We have SMB dialect 3.0, and we see, yeah. What brought me here actually is the fact that this is one of those fun ones that have the status buffer overflow, which doesn't, like, as far as I understand from the Microsoft documentation, doesn't really mean like buffer overflow. You know, it mostly just means that there's more binary data being pushed through the pipe than the pipe can handle. But it's still an indicator, because I see that, workstation to workstation name pipe communication is not really a thing. You would expect to see this kind of stuff more from the administrative side. You would expect your domain controller to be managing your workstation. You don't expect your workstation to be managing another workstation, right? And what can I read from here? Well, somebody has connected to another workstation, likely because they have already have the security context to do it. And then they are connecting to LSM API, which stands for Local Session Manager. You know, that thing in Windows that gives you an interactive desktop. And then you see a whole heap of pipes. So I'm pretty sure if we had a payload view here, we would just see like a full command line log in here. And overflow is just like probably too much data here. But that was an indicator that actually brought me here. Okay, now compromising DCs is something that was also mentioned in prior presentations. So what we can see here is something a bit more serious, because we see that there are successful pipe communication to the domain controller specifically. And here is something more interesting. So we see now this SMB DCERPC endpoint is something that is coming from our post-processing stack, but Peter can tell you way more. We have a rule set that will give you the same data. What does it mean when you get DCERPC remote procedure calls? Those calls have a UUID and opcode. Unique combination of that UUID and opcode can be translated to the actual administrative function that is being called on the system. And we have a rule set that will actually bring it, which is kind of an interesting concept. We're used to thinking about rules bringing out the data, but it can work in the reverse. Rules can actually be used to also enrich this kind of NSM data as well. So if I was using the open source rule set that does the same thing, then these function names would be in the metadata flow bits instead, right? And that's a and why do I like it? Because I can actually read a story here. Looks like somebody is basically doing user enumeration, connecting to the DC over name pipe. Literally, there's a function, lsr enumerator accounts of user rights. And then there's this repeating pattern here, which I think somebody's domain controller's user database just got dumped. That's my translation, at least as far as I'm reading the logs. And then nice polite disconnect at the end. What else can we see? How about this? So let's log in using NTLM SSB, NTLM password prompt, which is already kind of legacy because there should be Kerberos instead. So we see firstly a service account used, then an workstation internal account, and finally, oh my lord. How did I find it? Show me flow IDs with more than one distinct user authentication. Actually, it's like more than two, but yeah. And really, to kind of sum up, like how you can actually hunt in this is, first of all, what you really want to do, you want to drill in on some kind of an interesting field. Let's look at the users, for example. So NTLM SSB user. Look at some unique values here. I already see something here that has a really funky character encoding, right? So let's drill down on this. See, oh, only 4 flow IDs out of, well, small data set, 5,000 something. Let's inspect those. We can kind of like select which fields we want to inspect. Maybe I will add authentication data into the set, and yeah, and we can kind of see a pretty clear pattern of this really funky username being used. It's a login failure, which is actually another indicator, but there's a pattern here, so there's definitely some kind of a scripted malicious activity here trying to get into the system. Trying to move the show forward, you can see basically we have the same pattern for 4 different flow IDs. And this can actually also be very interesting because we're kind of used to think about flow IDs and correlating within the confines of a source destination IP. This is actually a pattern that you can kind of see bubbling out through the whole network because it can be one compromised host basically repeating this pattern over your entire domain. Maybe at a low volume if they actually know what they're doing, but trying to do this on multiple machines, which can again give you some patterns. Now, I need to apologize because I'm looking at the clock and I see that I really don't have much time to get into this, and this was literally a whole talk yesterday. But I just wanted to show you how you can, for example, use some of this data to do this, I don't like to use the word AI or ML. This is really just like really basic statistics and data mining. And my goal here, I'm going to be blunt, is to make pretty pictures and put some colors on them. Okay? So some suspension of disbelief. So I'm going to use a technique called k-means clustering. It is a very entry-level data mining algorithm that is widely used because it works. And it's actually kind of explainable. Idea is you have basically a set of coordinates. You drop k stands for the number of clusters you want. You drop random points at first. Then you measure the distance of every single data point you have to those central points. You assign them to clusters. You recalculate the central points for each cluster, and then you kind of like, you basically brute force it until the clusters don't change anymore. Sounds heavy, but actually it's super fast because it's all number calculations, and CPUs are kind of built to crunch numbers. So really it takes very little time. As mentioned yesterday in the ML AI presentation, Suricata data is mostly textual, so we need to transform it. How do we do it? We aggregate. Again, somebody brought out a few presentations ago that what does a security analyst like to do? We like to count things. So let's count things. So we select our features, which is something like SMB commands, SMB statuses, file name pipes, things like that. And then we build an aggregate data frame, so where we simply get the unique count of values, right? We can basically take our textual security data, the way that we're used to looking at it, which is oftentimes called atomic data, where, you know, like single indicators, single values, and we can transform it into a matrix like this, right? Which really gives us a different view of the whole thing. We can get a statistical view of here, but I'm not really going to focus on it too much. Another thing that was already mentioned yesterday is a technique called min-max scaling, which is probably one of my favorite techniques in data mining ever. If you're going to learn data mining for security, learn min-max scaling. Why? Because thresholding is really hard. What this technique does is, let's say you have a vector of counts, then you scale those counts to a range of 0 to 1. Why? It's the same data. The reason why you would do it is because if you consider the number of unique possibilities, then you can have tens or hundreds of thousands or millions of unique file names. You can have 20 unique SMB commands. The file names are going to win, right, if you leave the scales the way they are. But what you can do here is you can put them on the same scale. That is how you're meant to use it, but you can actually use this technique as a thresholding. Who has ever written a query something along the lines of, show me where the count is bigger than this number, and this number is something that I literally just came up with on the spot right now. Okay, it didn't work, let's try another number. Now let's try to put it into some kind of an automation system. Worked yesterday, didn't work today. Doesn't work in that network. How about you do something like, show me something where this normalized value is between 0.1 and 0.9. Let's drop the rare stuff. Let's drop the really heavy hitters. Show me in between, or show me at the bottom, or show me at the top, right? You can do this kind of stuff. Now I'm going to do something called principal component analysis, which I'm not going to get into because it's something that I can kind of get. I can be a little, I'm not going to tell you about how frustrated I am, how academics like to take this fairly simple concept and make it way more complicated than it is. Basically, we have something like 7 or 8 dimensions. Can't really put it on a 2D graph, but we can change the dimensionality. We can rotate the data points to the point where we only need 2 or 3 dimensions, and we can actually make this visible to humans, right? So this is what happened to our SMB data. And then we do the clustering itself, which, you know, as I said, my goal, make pretty pictures. That looks pretty enough to me. But we're not writing a research paper. This needs to be still kind of somehow usable to a hunter. So why would I use this? Well, if we map those cluster numbers back to the original data, we can aggregate based on the cluster. And all of a sudden, instead of inspecting 4,500 events, I am inspecting 6 clusters. If I look at some unique values here, some stuff might already pop out. So I can already see that there are some patterns that have been merged into the clusters. Now, the cluster numbers are always different, so it is non-deterministic. I will see what is actually coming out of it. Okay. So you can see that if I look at the unique file names in, let's say, the cluster 5, I have actually way more interesting stuff to look at. Why would that be interesting? Because if I compare that to, I think, what is the number here? 0. Yeah. This is what a GPO policy update looks like in Windows. As you can see, whole heap of basically file paths with the policy object UUID, which results in massive amount of unique file names you would need to inspect. So, but it's a pattern. those patterns can be correlated, they can be clustered, there are techniques to actually deal with this, to have something more reasonable to look at. And finally, I'm just going to show you another way how to view the data. Peter loves to refer to this picture lovingly as the Death Star. But we can also think of data in terms of, for example, a graph. So what I'm doing here is I'm connecting unique source IP to unique SMB statuses. And you might notice that not all of those statuses are actually labeled here. You can see the status success and all of the stuff in the center. Those aren't labeled. What am I doing? Where's the magic? Actually, it's very simple. What is a graph? This is not only for management porn. You can actually use this stuff. Graph is a set of nodes and a set of edges. Edge is basically a connection between two nodes. Now, each node has a very simple concept of degree. What is degree? Counting stuff. Degree value stands for number of connections that each node has. So all of a sudden, we can threshold again. So I did a completely arbitrary filter right now where the degree value is less than 3 because it's malware traffic analysis set. There's very little SMB there. It is a trivial set. But you can actually do something like that as well. So we can actually connect any two data points that we want. We can measure the number of connections. And why is this relevant, especially for SMB? Think how SMB is usually used in a corporate environment. You have some kind of a deployment of file shares sent out to your users. Your secretary only has a set of file shares automatically mapped for her. She doesn't have to configure anything herself. She's not going to go and configure new file shares for herself. There's some kind of a policy that will give her some set of shares, right? Now, which means if you start looking at, for example, how the users are actually using the resources and what is the overall pattern of the typical response codes, all of a sudden these kinds of funky things are become quite a bit easier to filter out. Something that you could do with data enrichment is something like, hey, let's map those IPs to known subnets and connect the subnet name to some kind of an SMB data point instead. Again, all of a sudden, you have a profile. And you can use this profile to actually do, let's say, you can almost think of this as kind of a rule, a non-deterministic rule that is more dynamic. It's not deterministic. You don't have a signature on a concrete packet, but you can kind of use this kind of a rule there. And I think it's really time for me to start shutting up, so I'm going to conclude the talk. This is actually a work in progress. As I mentioned, it's something that I've been kind of working on and off between other projects for a few years now. Every time we kind of look at this stuff with Peter and Eric, we always scratch our heads and raise our eyebrows and does nobody ever actually look at this stuff? The first time I looked at some of this stuff, Eric had a patch for SuriCata in 24 hours because of the funky status codes that weren't being mapped out. And every single time we kind of have a look at some of those samples, it's yep, okay. But anyways, don't think only about the alerts and atomic indicators. Your data can actually tell you a whole other story. And SMB data from SuriCata is insane. Compare that to something like Arkema, which I'm a very big fan of. You have one session. You have basically parsed out file names and maybe an SMB function, I think. That's it. It's one flow like any other. You don't get this granularity. Of course, Splunk users will complain about this granularity, but I like it. And with this, thank you. Ooh, I think I'm actually on time.
No questions? You guys good? You only have 45 minutes left, I promise. Okay, one question, hold on.
There was one.
Hi, thank you for the talk. I was wondering, you've been working on this for a couple of years now, you say?
Yeah, kind of looking into it on and off between our projects. So.
Yeah. Like, how would you use this? Do you maybe use this to, I don't know, find certain correlations that you otherwise wouldn't find? And maybe
so basically the main takeaways, and I'm shamelessly basically using this presentation to kind of like make myself work on it, is to kind of, first of all, low-hanging fruit, the statuses. Like, it's actually something that you really should have an eye out on your network. There are like really low-hanging fruits that can actually be very easily seen from there. Secondly, as I mentioned, building a profile. If you think in terms of how SMB is actually used, how file shares, how your map printers in a corporate environment are supposed to be used, there should be a fairly clear pattern, right?
as in like a baseline? Or?
Yes. So basically, I mean, you know, anomaly detection, you know, all of the sexy buzzwords,
Yeah,
but not resorting to something like a trained ML model that will work on your one specific data set, but actually something that is might work dynamically across multiple customers, right?
Yeah, and I think it's also, but I'm not, very well versed in the data science stuff. Like it also, what you showed with the file names, you can easily go through a large pile of data and still do quick analyses if you
Yeah, so the thing about these kinds of data mining techniques is that, well, I kind of, one of my goals here was really to, like, I know this is there are a couple of people here that are into data science, and everyone else who is not, and are used to using their Kibana dashboards. I kind of, having had like a PhD candidate and a researcher background, I kind of have my feet on the both sides. So it's something that I always want to do. I want to show people how to actually use some of this stuff. As I mentioned, like how I would use it is when talking about, for example, the graph degree value. The degree, like if you think about, forget about thinking about the graph as a picture. Graph, you can think of it as a matrix where you have like the source node, destination node, and the degree number is actually just another vector or another column within that same data frame. You can normalize that column. Again, you would have values between like 1, 20, 5,000, 100,000 if it's a GPO update, but you normalize it between 0 and 1. Then what you can do is, well, you can write a threshold, like show me stuff that is within like this, within this threshold, right? And it works differently depending on what the source and what kind of data we're talking about. There's like very high cardinality data, I would say. Honestly, that's the part where, you know, like looking into this over the course of many years kind of has its effect because I can't remember those specifics anymore. But at the end of the day, there are techniques you can use here to basically, and techniques from the very first pages, first sections of a data mining textbook to actually build pretty robust automation, like, hey, here's a set of flows that you might want to look into.
Yeah, okay, thank you.